I wanted to make sure that we got through this last example. So again, we're going to use variation parameters, but we're going to have to start by finding the solution to the complementary equation. So we're going to set y double prime minus 2y prime plus y equal to 0. And this is constant coefficient, homogeneous, so we're going to let y equal e to the rx. So we would end up with r squared e to the rx minus 2r e to the rx plus e to the rx equals 0. So we factor out our e to the rx and we're left with r squared minus 2r plus 1 equals 0. Since e to the rx cannot equal 0 because it's an exponential, we know that r squared minus 2r plus 1 equals 0. And this is a perfect square. This is r minus 1 times r minus 1. So that tells us that r1 equals r2 equals 1. And what we learned about this previously in this chapter is that when we have a repeated root, we know then that y1 is going to be e to the r1x, which is just e to the x, and y2 is going to be x e to the x. And we know we're going to have to find our Wronskian of y1 and y2. So let's do that. And we have e to the x for y1, whose derivative is e to the x. We have x e to the x for y2. So now this time we're going to have to use the product rule. So we'd have x e to the x plus e to the x. So the Wronskian here ends up being x e to the 2x plus e to the 2x minus x e to the 2x. So we end up with just e to the 2x. Well, first of all, we know this is never going to be 0, so our solution to the complementary equation is valid over all x, all real x. So we have it does form a fundamental set of solutions over all x. Then we have to move into our variation of parameters. So we know that our particular solution, yp, is u1, y1 plus u2, y2. So we know then also that u1 is equal to the negative integral of y2 times our forcing function g of x over the Wronskian of y1, y2 dx. Well, in this case, y2 is x e to the x times our forcing function is 14 x to the 3 halves e to the x, all divided by e to the 2x, which is our Wronskian. Well, an interesting thing happens then. We end up with our negative still on the outside. We have 14 x to the 3 halves times an x to the 1 makes it x to the 5 halves. And then we get e to the x times e to the x is e to the 2x, all over e to the 2x dx. Well, our e to the 2x's cancel, so we're really left with u1 being negative 14 times the integral of x to the 5 halves dx. Because like I said, our x squareds cancel out. E to the 2x's cancel out. So now we know how to integrate e or x to the 5 halves. We're going to add 1 to the power, so negative 14 times, add 1 to the power, x to the 7 halves, and then divide by that power, which is the same as multiplying by 2 over 7, which ends up giving us, well, what, negative 4 x to the 7 halves. So that was a lot easier than the last example. And u2, in this case, is going to be the integral of y1 g of x over the Wronskian of y1 g and y2 dx. So y1 is just e to the x. G of x is still 14 x to the 3 halves e to the x all over e to the 2x dx. Once again, we find out that we're going to have 14 x to the 3 halves, now e to the 2x over e to the 2x dx. So once again, our e to the 2x's cancel out. And we're left with 14 times the integral of x to the 3 halves dx. And again, we know that's going to be 14 times x to add 1, 5 halves, times the reciprocal will be 2/5. Or we get 28/5 x to the 5 halves. So now we know that our y sub p is u1 y1 plus u2 y2. Or negative 4 x to the 7 halves e to the x plus 28 over 5 x to the 5 halves times x e to the x. Well, now we can then combine those x's, because that's x to the 1. So we really get negative 4 x to the 7 halves e to the x plus 28 over 5 x to the, well, now 7 halves e to the x. So we can combine these. So we get essentially negative 20 over 5 plus 28 over 5. So we get 8 over 5 x to the 7 halves e to the x's. And that is our y sub p. So that is one of the things we were asked to find in this problem. So we found y sub p. We also want to know, excuse me, what the general solution is. So our general solution then would be y sub c plus y sub p, or c1 y1 plus c2 y2 plus y sub p. And in this case, that means y of x is c1 e to the x plus c2 x e to the x plus 8/5 x to the 7 halves e to the x. And that is our general solution.